Hello everyone, thanks for being here today. I want to talk about logging, specifically low overhead multi-threaded logging for low latency applications. I regret using this title because now I actually want to name this the art of not logging. Because in my opinion, a lot of people think the wrong way about logging. And that's what I'm here to talk about. So who am I? As already said, I'm Martijn Terpstra. I'm a manager for the Europe execution team. I work in the Amsterdam office, but we also have offices all over the world. So what am I talking about when I say execution at IMC? Execution is responsible for all the low latency applications. So mostly C++, and it's a cool name. So what we do, let's make it really simple. We just have a program, and most of our programs look like this. So we have a int main, we configure some stuff, and then all we do is we pull network buffers. So how does this make money? Well, there's an exchange. An exchange is a place where everyone can buy and sell stocks and other products. In order to know what shares are available to buy and sell, the exchange sends everyone, so not just us, network packets with what is happening in the markets. This is market data, and it's public data. Everyone that's connected to the exchange gets this packet. So let's take an example. We get a message that somebody wants to sell 4 shares of pair for €9. We pull a network buffer and we see, hey, we got a message from the exchange. This is very interesting. Let's look at this message and react as soon as possible. We think this is a fair price. So we send a message back. We want to buy this as fast as possible. 1 second. So let's convert this into a timeline. So we start all the way in the beginning with configure, then at some point our timeline starts with the start of this while running loop. So first, we start pulling network buffer, right? So this vertical bar means that. So let's take an example. The exchange sent us the example before, we sell pair for 5 shares for €9. So the order comes in, and we start reacting as quickly as possible. We decide this is a nice order, and we choose to buy it. Now that we've done the receiving and the sending, we know our total latency. This is what we want to have as quick as possible. So now we're done, and we're ready to pull for another order. So if we have logging overhead, and we are slower, then it might be that we're not getting the trade. So, okay, should we then never log in the hot path? That sounds dangerous to me. There's always something that's worthy enough of logging. Can we instead make the hot code cold and do it after the order? Not really, because after we're sending order, we might get a new message. And then we're not in time to pull the network buffer. So now we react too late, and this takes too long, and now the opportunity is probably already gone. So with this in mind, let's start making a logging framework from scratch. So who has not written something like this before? We all have, right? So this is a start, but a really bad start, because the out is slow and really old. Can we make this more modern? Of course. Now, who has written something like this? Nice, a few people. Yes, this is very new, but very nice, right? What much more readable. So let's continue adding on top of this. We just sent an error when it's over 9,000. Okay, but when did this happen, right? When we log, we want to know when stuff is happening. So stat format is to print, have this beautiful support for time point printing. So you just add %t, and now you can just make it print time of day. Awesome, now we know when it happens. Now we don't want to keep the user, force the user to send the order, We don't want the user to keep printing and making this now call. So, yeah, where was I? So we have the resolution clock, we get the timestamp, but now every single time you do a logging, you need to get the timestamp. That's not handy, so let's make a separate log function. So we call log, handle the timestamps there, but now we need to format twice, because the timestamp is the internal format, and we have the user string for the user format. So there's some overhead there. Also, instead of just getting a simple string, format expects a compile time constructed format string. So we need to ask the user to have a compile time value there as well. It's what we have to live with to be as fast as possible. Okay, next up, we have this error statement. And let's formalize it a bit, right? We don't want to manually keep typing error or warning everywhere. So let's move it into an enum value. And this already makes it a lot better. Now I can say I want to log with an error, and the timestamp is already in there. Now that we have a level, we can do the most important performance optimization for this entire presentation. We can not log. So let's implement not logging. So we get a global log level somewhere, and then we decide if we want to log. Awesome. So at the moment, it still prints. That's because error is a high enough severity level that it still needs to print. So we need to set the log level, and now it's fatal, and now the second time we're not printing. There we go. We've not logged for the first time. This is awesome. Let's look at the overhead. All we do is a compare and a jump. That's what we want. That's as fast as it can be. I doubt we can do faster than this. There's still something here that's slow though. And that's the passing of 9,000. Not in this scenario, but let's take this scenario. We have an expensive function that in the end returns 9,000. This can have all kinds of side effects, like throwing an exception if you have a lookup and it doesn't match. And then the side effects need to happen in case it is a thing. But now we don't print, but we still did the side effects. That's overhead we don't want. So how do we get rid of this? Unfortunately, well, we can try to pass a lambda, right? Then we evaluate later. That way, there's no overhead. And then when we see we do need to print, we invoke the lambda and then get the arguments. But now, again, we're pushing stuff to the user to make happen. So this is not really making things easy. So unfortunately, we have to move over to macros. It is what it is. It had to happen at some point. I know macros are evil, and I can only agree. But I think, in my opinion, logging and test frameworks are the only exceptions to this rule. So we introduce some scope with a do while, because we don't know, of course, what the rest of the scope is for the user. And then we get the level there. So let's make a macro per log level to also make it easier. And now we can also do another optimization. When we're in debug mode, or when we release mode, when we have a debug print, we don't emit anything. Because why would you enable debug logs in production? That sounds very dangerous to me. And if somebody makes a mistake, then all of a sudden the performance will go drastically down. Because usually debug logs are very spammy. So, now that we have this horrible macro with all this boilerplate, can we at least simplify some parts? Well, we can get rid of the std format string and pass the format as a template argument. Much better in my opinion. Another thing we can add now that we have a macro is the source location. Conveniently, the standard edit std source location. So the current function returns a const x per source location. Very handy, because now we don't need to use __ file and line. And there we go. We log the timestamp, source location, and the actual message. We now wrote a modern log macro that is using the modern format library. So let's dive a bit deeper into not logging. And what do I mean with that? I am really unhappy with this if statement, right? There's only a couple of log levels, and that's all you have to decide if to log or not. I want more granularity here. Because not logging is important. Of course, we want to log everything, but that doesn't work, right? The overhead is enormous. You would get spam. Log statements per level is an improvement, but still you miss the granularity. Everything either gets logged or it doesn't get logged at a specific level, which means that if you switch levels, you open the floodgates or you turn off entire sections of the code that's now not logging anymore when it's important. So what happens in a lot of production code bases is the log level gets stuck at a specific level. Everything's at info, everything's at notice or warning, and then everybody just programs their code just keeping in mind this log level, and then nothing actually happens. In my book, there's two types of log messages: important messages and unimportant messages. Important messages are things like warnings and errors. These are things you always want to print. Also, these are things where you want to make it easier in case something happens, or other configurations, like feature toggles or some settings. That's really nice to know. The unimportant messages, these are usually info and debug level, are more, usually you print the state of a project, right? Or of a component of a program. So it's really interesting if the program is running correctly, because if the program is running incorrectly, only then do you want to enable that. But you enable the log level, lower the log level, and now all of a sudden your floodgates open, right? We have all these logs we don't care about. So how do you enable unimportant logs without having log spam? We need path-based log levels. This way we can still set logs globally. We still want this because sometimes you just don't know what's happening. I just want everything. Give me everything. But we can use of our source folder structure to really choose our own granularity to say, hey, I want to log only my collections. I want to have, but you can still make it more high level. Hey, I have this top level folder util. Just give me everything in util that's a warning. And you can even narrow it down to a specific file. And in the case where you really want to have the specific state of something that's going wrong in your code. So you have something that's crashing, and it takes its brains because of this Boolean, and that's because of these parameters. I really just want to know this log statement because I know this log statement writes these states. Then you want to have the most granular way, which is file and line range filtering. So here with inline vector, everything between 55 and 90 should be debug level, and then we print anything that's in there. So what API do we want? When we log, we want to get the log level of the file and the line. And then when we set the logs, that's already what we discussed before. So let's look at this example. For instance here, global it's notice, collections is set to info, and we're really granular with inline vector. And now we can really decide, okay, inline hash map, that can be info, it's part of util collections. Inline vector with line 10, not part of the range, still keep it info. And then line 70 is inside the range, so we can make that debug. This way, we're only debug logging this specific line. Now we just need to implement this logic. So we already have a source location, so let's move that up. And then we need to adjust, of course, we don't no longer get a global log level. We now use the file name and the line to get an accurate log level. So let's take an main example. Here we go into it. We set the log level to fatal. And now we just want main CPP 70 to 20 to error. And hey, we log the error. Awesome. There's one glaring issue here though. This is really slow. There's no way you can make set log level and so wide and so narrow and look it up with file and line. You need even if with a crazy optimized O of 1 data structure, does it beat a compare and swap, compare and jump? No, it doesn't. So we're getting a lot slower. And if we get slower, we don't want it. We want to be fast, and we need to be fast. So let's make it static. Now we're at least slow the first time, but it's only the first time. Okay, what's the impact on the assembly? That's not great. It's not as bad, But still, we do a load, we do a compare, and we do another jump just for the static initializer. And we do this every single time. Only then in the bottom, we do the compare and jump we normally do. So let's brainstorm. So this is the program we had at the beginning, where we have in main, we configure and we do some running. So from the lifetime of the project, we have global initialization. Then we go into in main, and there we have configuration. And up to that point, we can be as slow as we want. We're just at a configuration stage. Then only when we hit it to while running, we need to be as quick as we can. And of course, in here, if we log the error, then we do the level lookup. And that's just really slow. We want to get rid of this. So where do we want to have this go? All the way to the top. Let's get some Boolean global initialized and look it up inside the log statements. Now we have a new problem though. Like this kind of lookup doesn't work, of course, because now at global initialization we get a log level, while in int main we're setting the log level. So what will it give? Only one default value, and then we set the log level and it does nothing. So we need to rethink the way we're gonna create this global level. So let's look at it like this. We'll have some way of having the metadata of a log statement and sort of initialize it and create this vector at the beginning of the program. Then when we go into int main, we set our log levels. We can still be slow here. And then we go over all the sources and we can do our lookup inside int main. And now we set should log everywhere for all the log statements. And then now when we're running, it's just a Boolean lookup. This would be awesome. So let's formalize this metadata at the top into a type. So we're having source here with a constructor and the three values we need, right? We need to level to compare it against the file and the line to look up the level we have configured. And this Boolean will be used to check if we're enabled. So let's insert it into our brainstorm. We have now a vector of source references. So we need to now still have this for loop give us these sources before main. How can we do this? For that, we need inline statics. Inline static variables are constructed during global initialization. And we need a unique source for every log statement that we have. So for that, we can make a sources struct that is templated on the file and line. And that way we instantiate a inline static for every log statement. So then the constructor happens before main. So what can we do in the constructor? We add ourselves to the list of sources. Now we have a completely constructed list of sources. We go into int main, we can go over it, and then we set the Boolean. So let's plug this sources thing into our macro. So instead of this static Boolean, we use std source location, and there we go. Now we get a reference to a global. We check for enabled, and then we log the format. So now we have a source object with the metadata of the log statement. Do we need to pass level and the current line and path? I think we can just pass source to the local. Makes it nice and simple. I log with this specific format. This is the source where we're going from, and then all the arguments that the user needs. Better. So how does the assembly look? This is what we want. Now we're back to just a compare and a jump. This is awesome. So to reiterate, I think full path level-based log filtering is really not the way to go. If you want to investigate something, you really want to be way more narrow. So use path and line-based filters to just increase your granularity. Because you can just do it with a single compare and jump. Now that we've covered not logging, we can continue on with the part where we actually are logging. So if we go back to the code, the explanation of the timeline, then we notice this cold code at the end. So then we get a message here, and we don't want that to happen. So we want to get rid of any cold code or any other overheads. Is there anything we can do? Because now we're reacting too late. So now we're back to the main program. We have our simple execution level program. We start, we configure, and all we do is pull network buffers. There's no room for cold code here while it's running. So let's put it on a different thread. So with a background thread, it will just be running and flushing any logs we make in our program. Now we need to efficiently offload as much as we can to this thread. How are we going to do that? With a ring buffer. So it's just going to be a single consumer, single producer ring buffer. Whatever we have in the logger macro, we want to offload as much stuff that needs to be computed. Mainly, of course, the call to std print line, because also I think it grabs some mutex. So the overhead is enormous, and we make that happen on the background thread. So for that, we use a ring buffer. We've everyone has seen a ring buffer before, right? So this is not interesting. The important part here is the function calls. So on the writing side, you can write it with a list of values you want to put in the buffer, and then you commit the write towards the flush logs thread. And then on the other side, if you want to read whatever you need to print, then you read from with a template argument, and then you commit the read to make sure that when you want to write, you can check, hey, do I have space? Did the background thread already flush this logs with a print? And of course, you want to know, is it empty? So the important part here is how do we get these values from the log macro into this buffer. So let's take an example message here. So now we have a runtime string to make it a little bit more interesting. I added a third argument as well. So in the bottom, you see what's currently being printed. What does it consist of? The timestamp, the source, the level, the arguments, and of course the format string. These can be categorized into two parts. The fixed part, which is the level, the source, and the format, we always notice at compile time before we do anything. And then we have the dynamic part, the timestamp and the arguments. This is what we need to compute and transfer onto the buffer every single time. Because if you look inside a template, the arguments are different if the template value is part of the argument. So we have the ring buffer here. We need to print the timestamp and the source, so we just binary put it in there, a timestamp and the source pointer. The format, same goes. Just const char pointer, because it's compile time, put it in there. Now we have a problem. How do we do the arguments? Like the integer and the double are already very simple, of course. You can just binary put those in as well. But how do we do strings? Also, we keep it really simple, actually. We just make a size, and we put in the data, the character data. And now we have encoded everything, and we can get it from. So let's produce these logs. So here we have a log statement, and now we're going to use the ring buffer. So we still need to get a timestamp. Then we get an instance of the log buffer. And then the ring buffer, we will write the timestamp, then the source, then the format, and then the arguments. And then, of course, when we're done pushing, we need to commit it so that the background thread knows, hey, it's available. There's a problem here. If we look at the format and the arguments, that's a const char pointer, and the arguments are binary encoded. Now we lose our type information. So is there a way we can still find a way where the background thread knows what to get, what arguments to get from the ring buffer? We use this nice hack called string pointer lambdas, by mistake. Because we have everything compile time at the moment, format and the argument types, we can just use a lambda that returns a string and takes a reference to the buffer, and then forward that to std format, and then later we can print that together with all the metadata from the internal string. So lambdas are implicitly convertible to function pointers. So now we can just write the function pointer instead of the format. So how do we get it? From the background thread, we also get an instance of the ring buffer. If it's not empty, we get all the metadata we need for our internal data, the timestamp, the source pointer. We now get this lambda pointer to the lambda function, we call the printer, and then we generate our user string. So then we invoke the printer with the ring buffer. Now that we have the user string and all the other data, we can print it on a different thread, and then when we're done, then we commit to the main thread that we're done. And now they know they have room again to create logs. So in summary, not logging is by far the most important part of programming your code. If you just use levels, then you have no visibility as soon as you get an error, or you need to change it and then the floodgates will open. Don't just use levels, make it more granular. And you can do it in a single compare and jump. And when you do actually log, offload as much as possible. Then that doesn't even only matter for logs. Think about any other type of metrics you're gathering. You can also offload those using the same solution. Because every nanosecond slower makes us less money. So logging has impact. Thank you all for your attention.